Hello, I'm Mohammad Alaee, research scientist from University of Luxembourg. Here, I would be happy to show you a demo for coexistence of radar and communication. Before going through the demo itself, I show the entire concept. We have two different systems for radar and communications together. We have a structure for co-design where radar and communications are working together with one hardware, and the other structure is coexistence. When radar and communication know that there are another system using the same frequency bands and try to work with each other kind of cooperatively. So in that sense, we are showing a demo here that shows that how radar can optimize its own transmit waveform. So this is the entire setup. I cannot bring that to the conference venue, but you can see that there are different antennas there, which are in principle sparse for transmitter and uniform for the receiver. 4 transmit antennas and 4 receive antennas, making a MIMO radar with 16 virtual antenna elements. They are connected to the USRPs, and this is a MIMO cognitive radar. Cognitive in a sense that radar can understand that when some interference is appearing in the scene, and based on that optimizing its own waveform. The right-hand figure here is the cognitive radar software that we have developed, and then the left hand is the spectrum analyzer. This spectrum analyzer observes if there is some interference in the scene and gives this information to the communication. Here we are showing a communication, base station and user is available in the scene. The red curve showing the throughput of the communication that it could be, but the green shows that the communication throughput that we are achieving. Whenever radar is operating in the scene, then we cannot achieve the maximum throughput of the communication. But when there is a cognitive radar in the scene, then the spectrum sensing application can sense the environment, and then based on that can give information to the radar itself. Radar based on that can optimize its own waveform that you can see right now it is going to be optimized. Then after optimization, you will see that suddenly improvements in the communication throughput happens, and you see that radar is not occupying the entire bandwidth, it's just occupying the bandwidths which are free in principle. So some updated version of this application is for the spectrum sensing is already implemented here. This is with C++, and all the parameters can be configured in the real time. For example, you can just change the operating frequency in real time to whatever you want. You can see that I'm just changing the operating frequency, and it is really using this hardware which is here. It is really kind of analyzing the environment. So this information is being transferred to the cognitive radar, which right now we have access to that remotely. And this cognitive radar, based on this information, optimizes its own waveform on the fly. To show that, we have emulated 2 different targets in different Doppler and then range beams. But you can also change the range beams of the targets, delays in real time. So you see that all the differences in the movement of both targets I can do. And then we are kind of evaluating the SNR radar, and then we can kind of change the waveform that we are transmitting based on different algorithms, different performance can be appear. So I hope that you have liked this demo. Thank you very much.